This steel monster still makes NATO admirals wake up in a cold sweat. It was given a truly sinister nickname, and Soviet geniuses wove technology into its DNA that literally breaks the laws of physics. How does this leviathan, weighing hundreds of tons, bypass the latest radar systems? Why does it need living transformer wings? And how can just one of its sorties send an entire fleet to the bottom? Today, our hero is the legendary and elusive Tu-22M3 bomber. Be sure to watch this video to the very last second. At the finale, I will reveal an exclusive inside look and share the shocking secret this giant is hiding from the entire world right now. Let's not delay, let's begin. 1949. The Soviet Union tested a nuclear device for the first time. The world changed overnight. But possessing such a device and being able to deliver it are two completely different questions. And it was this second question that became the main one for Soviet military strategists for the next 3 decades. On the other side of the ocean, the United States was building a fleet. Not just a fleet, they were building floating airfields. Carrier strike groups. Each such group was an aircraft carrier in the center, dozens of aircraft on board, and several cruisers and destroyers around it as a shield. Such a group could appear anywhere in the world ocean within 3 to 4 days. And no one could say no to it. In the 1960s, the United States had more than 10 such groups. This wasn't just a number. It meant that the coasts of Europe, Asia, and the Middle East were constantly within the range of American carrier-based aviation. An aircraft carrier isn't just a ship. It's a decision about who controls the sky over any shore on the planet. And at that moment, that decision was not being made in Moscow. Soviet strategists understood. Ground-based aviation was too slow. By the time a plane from a coastal airfield reached a carrier group in the open ocean, the group would already be in a different quadrant. Submarines are effective, but slow to react. Something else was needed. A plane was needed. Not just fast, not just long range. A plane that combined everything at once. Speed, allowing it to escape escort fighters. Range, allowing it to operate far from its own shores. And strike power, sufficient to ensure that a single strike could decide the outcome of an encounter with a group of warships. Such a plane did not exist anywhere in the world. In the late 1950s and early 1960s, Soviet aircraft designers worked with what they had. The jet bomber Tu-16 was a solid machine, reliable and proven. But its cruising speed of about 850 kilometers per hour made it vulnerable to the new generation of interceptors. It was built for a different era. And the era was changing rapidly. By the mid-1960s, American interceptor fighters were confidently operating at speeds exceeding the speed of sound by double. Surface-to-air missile systems were becoming more accurate and longer-ranged every year. High-altitude flight, which just 10 years prior was considered relatively safe, turned into a lethal risk. This was shown, in particular, by the incident with the American U-2 reconnaissance plane in 1960 over Soviet territory. The environment had changed, and Soviet aviation needed to change with it. The answer had to be a fundamentally new class of machines. A plane that flies low, below the radar, or flies so fast that the enemy has no time to react. Ideally, both, depending on the situation. It was here, in this specific military requirement, low or fast, depending on the circumstances, that the idea was born which ultimately led to the Tu-22M3. But before it was born, there was an attempt to solve the problem in a different way. A new plane was already standing in the hangars. It was called the Tu-22. On paper, it looked like a step into the future. In practice, everything turned out to be more complicated. The Tu-16 appeared in the sky in 1952, and for its time, it was a real breakthrough. 2 turbojet engines, swept wings, a maximum speed of about 1,050 kilometers per hour, a flight range of up to 6,000 kilometers. By the standards of the early 1950s, it was an outstanding machine. The Soviet Air Force finally received a jet bomber capable of operating over long distances. Tu-16s were built by the hundreds. They were in service in aviation regiments all across the Soviet Union. They were feared. They were respected. It performed its task. But time does not stand still, and by the end of the 1950s, military strategists began to see what was inconvenient to admit out loud. The Tu-16 was becoming obsolete, not because it had become worse, but because the enemy had become better. New generation American interceptor fighters, such as the Convair F-106 Delta Dart, by 1960 were confidently reaching speeds in excess of 2,000 kilometers per hour. The Tu-16, when encountering such an interceptor over the open ocean, had almost no chance of escaping. This was math, not an opinion. The answer was supposed to be the Tu-22. The Tupolev Design Bureau presented it in 1958. Externally, it was a completely unusual machine. Two engines were located not under the wings, as in the Tu-16, but at the base of the tail assembly, directly on the sides of the vertical stabilizer. This solution freed the wing from nacelles and allowed for a cleaner aerodynamic shape, a delta wing, a sharp nose. The plane looked aggressive and modern. At maximum speed, it accelerated to about 1,500 kilometers per hour. This was better than the Tu-16, significantly better. But the devil, as always, was in the details. The first problem was range. The practical range of the Tu-22 was about 4,900 kilometers. This is less than the Tu-16 it was meant to replace. For a plane intended for operations over the ocean, this is a serious limitation. The second problem was its behavior at low speeds. During landing, the Tu-22 required a very high approach speed, about 290 to 300 kilometers per hour. For comparison, modern civil airliners approach landing at speeds of about 240 to 260 kilometers per hour. The difference seems small, but in practice, it meant that the pilot had almost no room for error. Pilots who mastered the Tu-22 spoke about it openly. The machine was strict. It didn't forgive inaccuracies. It didn't forgive fatigue. It didn't forgive a moment's distraction on the landing course. Over the years of the Tu-22's operation, aviation lost several machines for this very reason. Not in combat, but during ordinary training flights. The third problem was perhaps the most unpleasant for military planners. Anti-ship missions. The main armament of the Tu-22 was the Kh-22 missile, which we will talk about in detail later. But for the effective use of this missile, the plane had to reach a certain altitude and speed, while finding itself in the zone of operation for ship-based surface-to-air missile systems. The equation didn't add up. By the mid-1960s, it became clear. The Tu-22 was not the solution. It was an intermediate step. Important, necessary, but intermediate. And then the main question stood in full scale. How to create a plane that works equally well at low speeds and at supersonic speeds, that takes off from a normal runway without requiring jewelry-like precision from the pilot, and yet is capable of reaching twice the speed of sound at high altitude. These two requirements contradict each other. Physically, a plane with a wing optimal for supersonic speed flies poorly at low speeds, and vice versa. When engineers first formulated this contradiction on paper, the solution seemed impossible. Until one person said, "What if the wing doesn't have to be the same in both cases? Take a sheet of paper, fold it lengthwise. It becomes narrow and rigid. Unfold it, it is wide and flexible again." This is, of course, a crude simplification. But this exact idea lies at the heart of one of the most elegant engineering solutions in the history of 20th century aviation: a variable sweep wing. It sounds simple. In practice, it is one of the most complex engineering tasks ever solved in aircraft manufacturing. Let's look at what happens to a plane at different speeds. At low speeds, during takeoff, landing, and flight at low altitudes, a plane needs a wide wing. A wide wing creates great lift. This allows flying slowly without falling. This is exactly why passenger airliners extend flaps before landing. They artificially increase the area and curvature of the wing. At supersonic speeds, everything is the opposite. A wide wing at such speeds is huge air resistance. The plane is as if trying to run a sprint while holding an open umbrella. For supersonic flight, you need a narrow, swept-back wing pressed to the fuselage. Minimal frontal cross-section, minimal resistance. 2 modes of flight, 2 different wings, 1 plane. Engineers proposed a solution that seemed almost absurd. What if we make the wing movable? What if we mechanically change the angle of its deflection right in flight, unfolding it for takeoff and landing, folding it for a supersonic dash? The idea was not entirely new in theory. Aerodynamicists had been discussing it since the late 1940s. But it is one thing to discuss it on paper. It is quite another to implement it on a combat plane weighing dozens of tons that must withstand colossal loads. The main technical problem was the wing pivot joint, the place where the wing attaches to the fuselage and around which it rotates. In flight, this joint experiences loads that make an ordinary mechanical engineer's hair stand on end. It must be simultaneously movable, so the wing can change its angle, and absolutely reliable, so as not to collapse under load at supersonic speeds. It's like making a door hinge that can withstand the weight of a freight train while opening with one finger. Soviet engineers worked on this problem at the Central Aerohydrodynamic Institute, an organization known in the aviation world by its abbreviation, but we will state it in full. The Central Aerohydrodynamic Institute, named after Professor Nikolai Yegorovich Zhukovsky. It was here, in the Moscow suburbs of Zhukovsky, that models were blown in wind tunnels, loads were calculated, and solutions were sought. And at approximately the same time, on the other side of the planet, the same questions were being asked by American engineers. In 1964, in the United States, the General Dynamics F-111 took to the sky. A tactical bomber with variable sweep wing geometry. The Americans arrived at the same idea independently, through their own calculations, their own wind tunnel tests, their own sleepless nights in design bureaus. 2 states, 2 completely different design teams, absolute secrecy on both sides, and the same answer to the same question. In science, this is called convergent evolution, when the nature of the task itself dictates the solution, regardless of who is solving the task. But here, it is important to understand one fundamental difference. The American F-111 was created primarily as a tactical aircraft, for operations at relatively short distances. Soviet designers set themselves a different task. A strategic aircraft capable of operating over the ocean, carrying heavy anti-ship weaponry, and at the same time, overcoming modern air defense systems. The scale of the task was different, and the scale of the machine had to be different. By the end of the 1960s, the concept had been developed. Technical solutions had been found. All that remained was the most important thing, to take responsibility and start building. This responsibility was taken by a specific person, the chief designer of the project. And the story of who he was and under what conditions he worked is a separate chapter, without which it is impossible to understand how this plane appeared at all. Andrei Nikolaevich Tupolev was born in 1888. When he was born, the Wright brothers had not yet built their first plane. When he passed away in 1972, Soviet aviation was one of the 2 strongest in the world, and a significant part of that path passed through his hands. Over his life, he designed more than 100 types of aircraft. 100. That is not a typo. But Tupolev's biography is not just a list of achievements. It is the story of a man who worked in conditions that are hard to even comprehend today. In 1937, at the height of political repressions, Andrei Tupolev was arrested. He was charged with high treason. He spent several years in custody and continued to work. The Soviet state, having imprisoned the country's best aircraft designer, simultaneously assigned him a task: to design planes, right in confinement, in a so-called sharashka, a closed design bureau for imprisoned specialists. He designed, because it was his calling, because there was no other choice, and because planes were more important than anything else. In 1955, Tupolev became the general designer. By that moment, he already had several decades of work, an arrest, rehabilitation, and post-war reconstruction of the aviation industry behind him. A man with such experience looks at technical tasks differently, without illusions, without unnecessary words. Only, what needs to be done and how? It was under his overall guidance that the project for a new bomber began. But the daily work of creating the specific machine fell on the shoulders of another person, Dmitry Sergeyevich Markov, the chief designer of the Tu-22M project. Markov joined the Tupolev Design Bureau as a young engineer. He went through the school of several previous projects, including work on the Tu-22. That is, he knew all the problems of the predecessor from the inside. He knew where the machine failed. He knew why. This knowledge became his main tool. The Markov team faced a task that was easy to formulate and almost impossible to solve. Create a plane that weighs more than 100,000 kilograms in a ready-for-combat state, takes off from a normal concrete runway, behaves predictably at low speeds, and forgives mistakes, and yet accelerates to a speed of 2,300 kilometers per hour at high altitude. For scale, 2,300 kilometers per hour is about 640 meters per second. In 1 second, the plane covers a distance equal to 6.5 football fields. At such a speed, from the moment a target is detected to the moment of flying over it, seconds pass. The Design Bureau's staff at that time numbered several thousand people. Engineers, designers, technologists, calculators, people most of whom would never be named in any official document. Their work dissolved into blueprints, into technical solutions, into rivets and welded seams of the finished machine. The state assignment did not provide for the right to fail. Deadlines were tight. Financing was targeted and strictly controlled. Every quarter, a report on progress. Every departure from the plan, an explanatory note signed by the manager. In such conditions, these people worked. Not in the silence of an academic laboratory, not in free creative search without deadlines. Within the rigid framework of a state program, where the price of failure was quite specific. And they succeeded. In 1969, work on the new plane, which received the internal designation Product 45-03, reached the final stage. The prototype was built. Systems were tested on stands. Engines were tested separately. The last step remained. On August 30th, 1969, at the flight test base in Kazan, the plane was rolled out onto the runway. The crew took their seats in the cockpit. The engines reached operating mode. What happened next defined the next half-century of Soviet and Russian military aviation. Kazan, August 1969, a city on the banks of the Volga, where one of the main aviation plants of the Soviet Union was located. The Kazan aviation plant, by that moment, already had a long history. Planes had been built here since the 1930s. The walls of the shops remembered both the war years, post-war reconstruction, and the jet era. Now, they were rolling out something new from these shops. The prototype of the first modification, the Tu-22M, which later received the more precise designation Tu-22M3, was already recognizable externally as a machine of another generation. In the extended position, the wing gave the plane a span of over 34 meters. Folded, about 23 meters, a difference of almost 1.5 times. And this difference was achieved mechanically, right in flight. The test pilot, Vasily Petrovich Borisov, took the controls of the first prototype. A test pilot is a profession that is difficult to describe in ordinary words. This is a person who is the first to sit in a machine about which no one yet knows how it will behave in the air. All calculations have been made, all test stands passed, but calculation and reality are different things. And Borisov knew this better than anyone. On the morning of August 30th, 1969, the engine warm-up took the required amount of time. Standing on the ground were members of the commission, engineers, designers, Dmitry Markov was among them. People who had spent several years at the blueprints of this machine were now simply standing and watching. There was nothing more to do. Everything that depended on them had already been done. The plane began its takeoff roll, a long concrete runway. The increasing roar of two turbojet engines. A machine weighing over 100,000 kilograms was gaining speed, and those standing near the runway felt this sound not with their ears, but with their whole bodies. This is not a rumble, it is pressure. The physical pressure of sound waves on the chest. The wheels left the concrete. The plane rose. In the air, Borisov performed a series of maneuvers according to the set program, changing the wing sweep in flight, a key element of the test. The mechanism, which was to work for thousands of hours in the most varied conditions, worked for the first time exactly as it was calculated. The wing folded. The wing unfolded. The plane, at the same time, continued to fly steadily. The flight lasted about half an hour. When the machine landed and the wheels touched the runway again, people on the ground breathed a sigh of relief. Not because they were afraid of a catastrophe, just because the first flight of any new plane is always a moment when years of work are checked in 30 minutes. And those 30 minutes always seem very long. Borisov taxied to the parking area. The engines went silent. He got out of the cockpit. Markov approached him. "Does it live?" he asked. Borisov paused for a second, not because he didn't know the answer, just because such moments do not tolerate haste. "It lives," he said. That was enough. But the first flight is not the finish line. It is the beginning of a long journey, which in aviation is called a test program. Borisov lifted the machine into the air. Now it remained to find out everything else. How it behaves at limit modes, how the armament works, where the boundaries of the possible are, and where the boundaries of the permissible lie. The test showed the main thing. The concept works. Variable sweep wing on a machine of this class is not theory. It is reality. But they also showed something else. It was still a long way from being a combat-ready machine. The first prototype was raw. The engines did not provide the calculated thrust. The avionics required serious refinement. A number of systems worked unstably. The engineers returned to the blueprints. Thus began a path that took almost 8 years, from the first takeoff of the prototype in 1969 to the appearance of that machine which the whole world came to know under the name Tu-22M3. And every step of this path is a separate story about how good becomes the best. In aviation, there is an unspoken rule. The first machine is never the last. This is not a flaw in the system. It is the very nature of complex technology. When a plane takes to the air for the first time, engineers receive information that is impossible to get in any other way. Only a real flight shows where the calculation coincided with reality, and where it diverged. And it is this divergence that becomes the material for the next step. After the first flights of the Tu-22M3 prototype, it became clear. The direction was chosen correctly, but there was still much work to do. The engines on the prototype were NK144-22S, a forced version of the engines originally developed for the Tu-144 passenger supersonic plane. A forced solution. The necessary engines were not on hand, so they took what was available. But these engines did not provide the thrust required for a combat machine. They were heavier than necessary. They consumed more fuel than was permissible. Range suffered. And range for a plane intended for operations over the ocean is not a secondary parameter. It is the meaning of the machine's existence. Parallel to this, other things became clear. The mechanism for changing the wing sweep worked, but required refinement of the mounting points. At certain flight modes, vibrations occurred that were not predicted by calculations. Radar equipment needed to be replaced with more modern versions. The list was long. In 1971, the first refined modification, the Tu-22M1, went into series production. Formally, it was no longer an experimental, but a serial machine. But the military, having received it, quickly realized this was still an intermediate variant. The Tu-22M1 was built in a small series, about 9 machines. They were used mainly to continue the test program and develop tactical techniques. The main result of this stage was that engineers understood exactly. New engines were needed. Fundamentally different ones. Working on this task was the design bureau of Nikolai Dmitrievich Kuznetsov, one of the leading Soviet developers of aircraft engines. It was Kuznetsov's engines that stood on the N-1 launch vehicle in the lunar program. It was his team now that had to give Markov's plane the heart it needed. In 1972, the Tu-22M3 modification appeared. This was already a serious machine. New NK-22 engines provided a noticeable increase in thrust. The navigation system was completely redesigned. The armament control system was improved. The plane received a new targeting complex that allowed for much more precise use of missile weaponry. The flight deck was redesigned based on pilot comments collected over years of testing. The Tu-22M3 was built in significantly larger numbers, about 211 machines. It entered service with aviation regiments and began to be practiced in conditions close to real. But the engineers did not stop, because the military's requirements also did not stand still. The American fleet was getting stronger. Air defense systems of naval formations were becoming better. Surface-to-air missile systems on aircraft carriers and escort ships received new radars, new guidance algorithms, and increased range of destruction. Each improvement on that side required a counter-improvement on this one, and the answer was ready. On June 20th, 1977, a machine took off over the Kazan airfield that became the final answer to all the questions accumulated over 8 years of work. The Tu-22M3, the third and final main modification. The very one that in the West would be given a name that became a household word. What changed compared to its predecessor is not just important. It is fundamental. NK-25 engines instead of NK-22. An increase in thrust on afterburner, substantial. Maximum speed grew to 2,300 km per hour versus 1,800 for the Tu-22M3. New air intakes, redesigned, more efficient at high speeds. A completely updated targeting navigation complex. A new electronic warfare system. Combat load, up to 24,000 kilograms. To understand this figure, it is the weight of approximately 16 medium-class passenger cars. All this on internal and external suspension points. Practical range without refueling, about 7,000 kilometers. Combat radius with maximum load, about 2,400 kilometers. It was precisely with the appearance of the Tu-22M3 that it became obvious. The task set in the late 1960s had been solved, completely, with a margin. But every legend has a heart, and in this machine, it beat at a frequency that you didn't hear, but felt with your whole body. 2 NK-25 engines, a product that deserves a separate conversation. Take a fire, an ordinary fire of dry wood. Now take a powerful pump and start forcing compressed air into this fire. The flame will flare up brighter. The temperature will rise. Energy is released faster. Now do the same, but instead of a fire, a stream of kerosene instead of a pump, a turbojet engine compressor instead of a log pile, a combustion chamber made of heat-resistant alloys. Add an afterburner, an additional section behind the main turbine, where more fuel is injected directly into the white-hot stream of exhaust gases. The temperature in the afterburner chamber rises above 1,500 degrees Celsius. This is the NK-25. The engine was developed at the Nikolai Kuznetsov Design Bureau in the city of Kuybyshev. Today, this city is called Samara. Work on it proceeded in parallel with the refinement of the plane itself. Kuznetsov's engineers understood. They needed to create an engine that would work reliably in a very wide range of conditions. From takeoff mode at an airfield, where the air temperature can be -30 and +40, to cruising flight at an altitude of 13,000 meters, where the temperature outside drops to -55 to 60 degrees Celsius. One NK-25 engine at maximum afterburner develops thrust of about 245 kilonewtons. On the Tu-22M3, there are 2. Total thrust in afterburner mode, about 490 kilonewtons. A kilonewton is a unit of force. Not to operate with abstract numbers. 490 kilonewtons is approximately the effort with which 50,000 kilograms press on scales. This force pushes a machine weighing 124,000 kilograms forward and accelerates it to a speed twice the speed of sound. The speed of sound at high altitude is about 1,060 kilometers per hour. The Mach number is the ratio of the plane's speed to the speed of sound in given conditions. The Tu-22M3 at high altitude reaches a Mach number of 2.1. That is, it flies about twice as fast as sound travels in the air around it. What this means physically is important to understand correctly. At such a speed, the plane outruns its own sound. This means that an observer on the ground first sees the plane and only then hears it. The sonic boom, a sharp clap that is heard when a supersonic plane flies over an observer, is not the sound of the engines. It is the sound cone, a shock wave of compressed air that the plane drags behind it like a wave behind a ship. But a sonic boom is what is heard from the outside. Inside, something else happens. At a speed of about 2,300 kilometers per hour, the air in front of the nose of the plane does not have time to part. It is compressed, and this compression turns into heat. The nose cone, the leading edges of the wings, the engine air intakes, all this in full afterburner heats up to a temperature of about 100 to 120 degrees Celsius. It is not glowing red-hot metal. It is just hot metal. But if you put your palm to it, the burn will be immediate. The fuselage in flight literally expands from the heat by a few centimeters. This is built into the design. The engineers provided for this. Now, what the crew feels. In the cockpit of the Tu-22M3, there are 3 people: the aircraft commander, the navigator operator, and the weapons systems operator. Their workstation. These are ejection seats, instrument panels, screens, control handles. The cockpit is pressurized. The air conditioning system maintains normal pressure and temperature. But you cannot fool physics. Upon entering afterburner, G-force presses the crew into their seats. Not sharply, smoothly, but persistently. During an energetic maneuver at high speed, the G-force can reach several units. Each G-unit is an additional weight of your own body. At 3 Gs, a person weighing 80 kilograms feels like 240 kilograms. The noise in the cockpit, even with the canopy closed and in the helmet, is not background hum. It is a constant presence. Vibration is transmitted through the plane's structure. The pilot's hands on the control stick feel every change in engine mode. At cruising altitude, it is minus 55 degrees outside. Inside, it is a normal temperature. Between these two worlds, a few centimeters of skin and the cockpit canopy glass. Pilots who underwent training on this machine said the same thing. The Tu-22M3 requires full presence. Not 90% of attention, not 95, exactly 100. In this cockpit, there is no place for extraneous thoughts. The machine feels it and reminds you immediately. But all this is a delivery vehicle. The main question was always different. What exactly is this machine carrying to the target? There are planes that are weapons in themselves, and there are planes that are platforms, a means of delivery to the point of application. The Tu-22M3 belongs to the second category, but it is such a powerful platform that the boundary between these two concepts becomes blurred. Let's start with the main thing, the KH-22 missile. In documents and reference books, it appears under the name Storm. This is not a metaphor for a catchy phrase. It is an exact description of what happens after its launch. The KH-22 was developed since the late 1950s at the design bureau of Alexander Yakovlevich Berezniak. The task was formulated quite clearly. Create a missile capable of hitting a large surface ship, primarily an aircraft carrier, from such a distance that the carrier aircraft is outside the zone of fire of ship-based anti-aircraft complexes. This requirement determined everything. The missile turned out to be large, very large. Length, about 11.6 meters. For comparison, this is approximately the height of a 4-story building. Wingspan, about 3 meters. Launch weight, about 5,900 kilograms, almost 6 tons. 6 tons. This is the weight of about 4 medium-class passenger cars. And the Tu-22M3 carries this missile on an external mount under the fuselage, one on the central pylon, and takes off with it, accelerates, and reaches a combat course. The missile engine, liquid fuel rocket. After release from the carrier plane, the KH-22 accelerates to a speed of about 4,000 kilometers per hour. This is about Mach 3.6, faster than the plane itself flies. Launch range, depending on the modification and mode of application, from 140 to 600 kilometers. This means the plane can perform a launch while far beyond the horizon from the target. Ship-based radars at the moment of launch may not see the carrier at all. They will see only the missile itself, and it will already be too late. On the approach to the target, the KH-22 descends to a low altitude and performs the final stretch of the trajectory almost at the surface of the water. This further complicates its interception by ship-based anti-aircraft complexes. A low-flying target at a speed of over 4,000 kilometers per hour is an extremely difficult task for any air defense system of that time. The warhead, according to various data, about 900 to 1,000 kilograms. In the variant for destroying ground targets, a special warhead could be installed. The details of this variant were not disclosed in open sources. The second missile in the Tu-22M3's arsenal is the KH-15. Developed by the Raduga Design Bureau in the city of Dubna, a completely different concept. If the KH-22 is a heavy strike from a long distance, the KH-15 is speed and surprise. The missile is significantly smaller, length about 4.8 meters, launch weight about 1,200 kilograms. However, the speed after launch reaches Mach 5. This is about 6,000 kilometers per hour. Such a target is practically impossible to intercept with air defense systems that existed during the period of its creation. The KH-15 was developed in several variants: anti-radar, for suppressing enemy radar stations, and strike, for destroying ground and surface targets. The Tu-22M3 could carry up to 6 KH-15 missiles on an internal rotary launcher, plus additional ones on external suspension points. 6 missiles with a speed 5 times the speed of sound. A simultaneous volley of such a complex presented a task that air defense systems of that time could not handle in principle. Now, the final image. The maximum combat load of the Tu-22M3 is 24,000 kilograms, 24 tons. This is the weight of approximately 16 medium-class passenger cars. Or, if talking about free-fall bombs, this could be several dozen 500-kilogram aerial bombs, placed in bomb bays and on external suspension points. 1 plane, 3 people in the cockpit, and such a load on board. When in the West in the early 1970s, intelligence services began to receive the first reliable data about the capabilities of this machine, the reaction was predictable. It was not quiet. In the code designation system of the North Atlantic Treaty Organization, every Soviet plane received a name in English. Bombers, names starting with B. Fighters, names starting with F. Transport planes, names starting with C. This was a working system of classification, convenient for staff officers and analysts. The new Soviet bomber, with variable sweep wing geometry, was assigned the designation Backfire, in literal translation, backward fire, or, if looking for a more accurate semantic equivalent, fire striking back. The name turned out to be accurate. Western intelligence services received the first data about the new Soviet plane in the early 1970s. Sources were different: satellite images of airfields, intercepted negotiations, human intelligence data. The picture was forming gradually, like a puzzle that at first only has corner pieces. American analysts at the Central Intelligence Agency and the Defense Intelligence Agency work with this data methodically. Wingspan, determined from satellite images. Engine location, recorded. Fuselage length, calculated by the ratio with known objects on the airfield. But the most important thing, flight range, remained a subject of debate for several years. And it was precisely this dispute that became the center of one of the most tense diplomatic confrontations of the Cold War era. In 1972, the Soviet Union and the United States signed the Strategic Arms Limitation Treaty, the first one. This agreement limited the number of intercontinental ballistic missiles and ballistic missiles on submarines. Strategic aviation was not included in it. The parties agreed to return to this issue later. Later arrived in 1974, when negotiations for the second treaty began, the Strategic Arms Limitation Treaty 2. In here, the American side put the issue squarely. The Tu-22M3 must be included in the list of limited strategic systems. The Americans' logic was as follows. If a plane is capable of flying from the territory of the Soviet Union to the territory of the United States, even in one direction without return, it is a strategic carrier, and its number must be limited. The Soviet side objected. Official position. The Tu-22M3 is a medium-range aircraft intended for operations in the theater of military operations in Europe and over adjacent maritime areas. Not intercontinental, not strategic in the sense that the Americans put into this word. The dispute went on for several years, at the level of ministers, at the level of heads of state. In 1979, the Strategic Arms Limitation Treaty 2 was finally signed. The Tu-22M3 was not included in the list of strategic carriers, but the Soviet side took on a number of obligations. Limit production of the plane to 30 machines per year, and not equip it with an in-flight refueling probe, which significantly limited its practical range. An in-flight refueling probe. This is a small detail, a retractable tube in the nose of the plane through which fuel is received in flight from a tanker plane. On early modifications of the Tu-22M, it existed. On the Tu-22M3 in serial production, it was removed, precisely as a fulfillment of a political obligation. But while diplomats were discussing probes and ranges in Geneva's negotiation halls, American military planners were doing their job. The deployment doctrine of carrier strike groups was revised. Aircraft carriers began to stay further from potential zones of operation of Soviet naval aviation. The calculation was simple. If the Tu-22M3 has a combat radius of about 2,400 kilometers, the carrier group must be outside this radius under any circumstances. One plane changed the geography of the American fleet. This is not a metaphor. This is a documented fact of military planning. Northern Atlantic, Norwegian Sea, Mediterranean. Zones where American aircraft carriers traditionally operated relatively freely now required separate calculation of threats. In every operational plan, a line appeared. Threat from Soviet long-range naval missile-carrying aviation. In NATO headquarters, the Tu-22M3 began to be called simply Backfire, without decoding. Everyone understood what was being talked about. The very fact that this plane became a subject of negotiations at the highest state level, a subject of special points in international treaties, and a basis for the revision of military doctrines, speaks more about it than any technical characteristics. But behind all these geopolitical consequences, it is easy to forget one thing. Every time this plane appeared in the sky, there were 3 people in the cockpit. Not doctrines, not treaties. People. Test pilot Vasily Borisov lifted the first prototype into the air, alone, in the sense that it was his hands that held the controls. But a combat machine does not fly that way. The Tu-22M3 is a crew aircraft. 3 people, 3 completely different specialties, and 3 completely different views of the same machine. Aircraft commander. His workstation, the left front seat. In front of him, an instrument board with dozens of indicators, a control handle, pedals, engine control levers. The commander is responsible for the machine as a whole, for takeoff, for flight along the route, for landing, for decisions that are made in seconds and have no right to be wrong. Preparation for a Tu-22M3 commander took years. First, flight schools. Then, flight hours on training and transition types. Then, gradual mastery of the plane itself. First with an instructor, then independently. Total flight time by the moment of admission to independent flights on the Tu-22M3 was calculated in the hundreds of hours. And still, the machine did not forgive complacency. Navigator-operator, right front seat. His task, navigation. To know at every moment of the flight the exact location of the plane. To calculate the course. To monitor fuel consumption. To maintain time parameters of the route. On a plane flying at a speed of 2,000 plus kilometers per hour, A navigation error of 1 minute is a deviation from the course of more than 30 kilometers. 30 kilometers for 1 minute of inattention. The navigator worked with a navigation complex that included an inertial navigation system, radio navigation equipment, and astronavigation instruments. In conditions of radio silence, when the use of radio communication in radio navigation is prohibited for reasons of stealth, the navigator had to lead the plane by the stars and inertial sensors. Just as navigators did on ships several centuries ago, only at a speed that the navigators of those ships could not have dreamed of. Weapons Systems Operator, rear seat. His working moment comes when the rest of the crew has already done theirs, brought the machine to the boundary of armament application. Now it is his turn. Radar targeting complex, target acquisition, calculation of the moment of launch, command for the application of armament. All this in conditions when the plane can perform evasion maneuvers, when enemy electronic warfare assets are working, when every second counts. 3 people in one cockpit, and yet each of them exists in their own professional world. The crew's cohesion was worked out over years of joint flights. Pilots who served together for several years understood each other without words, by the change in the tone of voice in the intercom system, by the nature of movements in the cockpit, by how someone reached for a toggle switch a little faster than usual. This is not an exaggeration. This is the professional reality of long-range aviation crews. Flights on the Tu-22M3 were physically heavy. The duration of a combat mission, considering the route, reaching the line of armament application, and returning to base, could last several hours. Several hours in a seat with an ejection system, in an oxygen mask at high altitudes, in the constant noise of the engines, under the pressure of responsibility for the machine and for the people nearby. Long-range aviation pilots rarely talk about this publicly. Professional culture does not involve complaints. But in rare interviews that still happened, veterans spoke about one feeling invariably: respect for the machine. Not fear, not attachment in a sentimental sense. Exactly respect, as for something that requires full dedication and answers with the same. One of the veterans who flew on the Tu-22M3 in the 1980s described it this way: "You sit in the seat, and the machine feels it. If you are not ready, it will tell you about it in the first minutes. Not with words, but it will tell you." This is the relationship between pilot and plane, which is not described in technical manuals, and which is not transmitted by any numbers or characteristics. But all this is preparation, theory, doctrine, exercises. Real verification comes when conditions cease to be academic. For the Tu-22M3, such a check came over the mountains, over very specific mountains. Afghanistan, a mountain country in the center of Asia. The average altitude of the terrain is about 1,800 meters above sea level. Mountain ridges reach 7,000 meters. Narrow valleys between them, sometimes a few kilometers wide, sometimes a few hundred meters. The air is thin. Turbulence is unpredictable. Weather changes quickly. This is not the landscape for which the Tu-22M3 was designed. The machine was created for open spaces, for the North Atlantic, where from horizon to horizon, only water and sky. For reaching a carrier group in the open ocean, where there is no terrain, no populated areas, no narrow corridors between cliffs. There, the plane felt in its element. Wide space, room for maneuver, predictable environment. The Afghan mountains were the exact opposite. Soviet air forces began using the Tu-22M3 in Afghanistan in 1988, at the final stage of the Soviet troops' presence in the country. The task was formulated in terms that aviators call working by area, delivering bombing strikes on large zones of high-altitude terrain from high altitudes. It was here that one of the key qualities of the machine manifested itself, which is not always mentioned in the first place: the high practical flight altitude. The practical ceiling of the Tu-22M3 is 13,000 meters, 13 kilometers above sea level. At such an altitude, the plane is above most mountain ranges of Afghanistan, above the zone of effective use of man-portable air defense systems, which the opposing sides had. In fact, in inaccessibility for the means of counteraction available in those conditions. But altitude created its own problem. From an altitude of 10,000 to 13,000 meters, precision bombing is a completely different task than from an altitude of 500 meters. A bomb dropped from such an altitude flies for several dozen seconds. During this time, it shifts from the point of release under the influence of the wind, which at different altitudes blows at different speeds and in different directions. Calculating the release point considering all these factors is a task for the targeting complex and the navigator simultaneously. The targeting navigation complex, abbreviated in documents as the Targeting Navigation Unit, on the Tu-22M3, was designed primarily for the use of missile weaponry. High-altitude bombing of ground targets in mountainous terrain required the development of new tactical techniques directly in the course of practical work. This is what in aviation is called mastering combat experience. Crews returned to base, conducted debriefings, analyzed results, corrected the methodology, and took off again. The flight time that accumulated in Afghan conditions was special. Mountain terrain created turbulence on the approach to the bombing zones. Thin air affected aerodynamics at low speeds, although at high altitudes, the Tu-22M3 practically did not feel this. Heat in the summer period at Afghan airfields used for intermediate basing affected takeoff characteristics. Hot air is less dense, lift is less, takeoff roll is longer. Each of these factors is a separate line in flight manuals, which were rewritten based on the results of real flights. One of the officers who participated in those sorties recalled later, "The first thing that struck one when working over Afghan terrain was the silence in the cockpit before exiting to the release boundary. Not because there was nothing to say, just because every crew member at that moment was doing exactly what they had to do, without unnecessary words. The machine and the people worked as a single whole. This is the highest evaluation of crew cohesion, not a certificate, not a record in a personnel file. Silence in the cockpit, in which everyone knows their job." The Afghan experience gave aviation engineers and tacticians data that could not be obtained at a test site. It showed where the machine works exactly as intended, and where it requires further development. By the moment when the last Soviet planes left the Afghan sky in 1989, the Tu-22M3 had passed a check that no technical specification had provided for. It succeeded. And then came 1991. And the world in which this plane was created ceased to exist. The Soviet Union ceased to exist. The army, fleet, and aviation that it served were divided between new states. Financing was cut by many times. Plants stopped. Programs were closed. Many planes of that era did not survive this transition, were parked, were cut into metal, disappeared. The Tu-22M3 remained. In 1991, the Soviet Union ceased to exist. 15 new states divided among themselves the army, fleet, aviation, debts, and assets of a huge country. This was not just a political process. This was the dismantling of an entire civilization, with all its equipment, infrastructure, and people. Aviation fleets were divided on a territorial basis. What planes were on which airfield at the moment of the collapse? Those remained in that country. Part of the machines ended up in Ukraine, part in Russia, part in other republics. Financing of Russian armed forces in the 1990s was cut so much that maintaining complex aviation equipment became a genuine challenge for technical services. Spare parts were in short supply. Fuel was allocated in minimal volumes. Pilot flight time fell to levels that in Soviet times would have been regarded as an emergency situation. In these conditions, many aviation systems of the Soviet era quietly left the scene, not as a result of combat losses, not because they were replaced by something better, simply because maintaining them became impossible. The Tu-22M3 held its ground, and this in itself requires explanation. There were several reasons. First, the machine had no equivalent replacement. Russian long-range aviation was built around several key types of planes. The Tu-22M3 occupied its niche, naval missile carrier and long-range bomber, and there was nothing to replace it with. The development of a new machine in the conditions of the 1990s was financially impossible. Second, the plane was built reliably. The Kazan aviation plant produced the Tu-22M3 with high assembly quality. The plane's airframe had significant resources. With competent technical maintenance, it could be operated for decades. Third, people. Technical specialists who maintained these machines maintained continuity. Knowledge was passed from the older generation to the younger. Not always officially, not always by textbooks. Sometimes just in a conversation in a hangar, at a specific unit of a specific plane. This is the live transfer of experience, which cannot be digitized and which is very easy to lose. It was not lost. In the 2000s, when financing of Russian armed forces began to recover, the next step became possible: deep modernization. The plane, created in 1977, received 21st century avionics. The modernized variant received the designation Tu-22M3M. The letter M at the end means modernized. In the Russian aviation tradition, this is the standard designation for an updated version. What changed in the Tu-22M3M is fundamental. A new targeting navigation complex based on modern electronic components. Digital flight control systems instead of analog ones. Compatibility with new generation precision cruise missiles. Updated electronic warfare assets. New screens in the cockpit instead of the Soviet-era analog gauges. The airframe is the same. The engines, the same NK-25s, which underwent major overhaul and resource extension. But inside is a machine that speaks to modern systems in a modern language. The first modernized plane took to the air on December 16, 2018, almost 50 years after the first flight of the prototype in 1969. 50 years. To understand this term, when in 1969 the first prototype took off from the Kazan runway, man had not yet set foot on the moon. This happened a few weeks later, in July of the same year. Since then, several generations of computers have changed. Mobile phones have gone from non-existence to supercomputers in one's pocket. The internet has changed the structure of human civilization. And the plane continues to fly. This is not conservatism. This is not a lack of desire to change. This is evidence that the fundamental engineering solutions laid into the machine in the late 1960s turned out to be so correct that time did not make them obsolete. Variable wing sweep still works. Airframe layout is still aerodynamically efficient. The concept of a long-range missile carrier is still in demand. Andrei Tupolev did not live to see the appearance of the Tu-22M3. He passed in 1972, 5 years before the first flight of this modification. But he managed to see that the path chosen by his design bureau was correct. Dmitry Markov, under whose leadership this machine was created, lived long enough to see. His work outlived the era that gave birth to it. There is something more in this than just technical history. The story of the Tu-22M3 is a story about what happens when people take on a task that seems impossible and do not retreat. When engineers work in conditions of extreme pressure and find solutions that turn out to be eternal. When pilots sit in the cockpit of a machine and establish with it relationships that are not described in any manual. This is a story about people. The plane is only the material incarnation of their labor. There are machines that perform a task, take off, fly, land, serve the required term, and leave. They are remembered only in archives and in museum exhibits. And there are machines that become an era, which outlive the countries that created them, which are modernized and continue to fly when they were long predicted for decommissioning, which force the revision of military doctrines, become a subject of international negotiations, and remain in the ranks half a century after their first flight. The Tu-22M3 is from the second category, not because it is the fastest of those ever created, not because it is the only one in its class, but because behind every welded seam of its fuselage, behind every bolt in the wing pivot joint, behind every line in its onboard documentation, stands the story of people who believed in one simple idea. Impossible is just something that hasn't been done yet. They did it, and the machine flies.